So, that brings us to a particular question, how to find these conjugate points. The moment we are able to find these conjugate points, we are guaranteed that the extremal that we have will be neither a minimum or a maximum. Okay. So, this question now reduces to how to find the conjugate points. Okay. So, that is what we are going to describe next. So, we start with y, our solution y being an extremal or the solution to the Euler-Lagrange equation. So, suppose I have already evaluated the first variation and found that y is my extremal. So, y is a general solution to my Euler-Lagrange equation, right. So, let me write this down, partial f partial y prime minus partial f partial y is equal to 0, right. Okay. Y is a general solution to the Euler-Lagrange for the functional j of y, which is the fixed point functional. Okay. So, then I know that this Euler-Lagrange equation in general is a second order, it is a second order differential equation, right. So, we expect that we are going to get two linearly independent solutions in general. Okay. So, the general solution to my Euler-Lagrange equation is, since this is a second order ODE, the general solution contains two parameters, right. It contains two parameters or my integration constants. The general solution contains two parameters or integration constants, which means that my general solution can be written as follows. So, I have y, which is my general solution to the Euler-Lagrange, is a function, or of course, it is a function of the family of these two parameters C1 and C2, right. So, what have we got? So, what we have is, so which means that, so y is an extremal, or so plugging back y into my f, right, which is the integrand, plugging back my y into f, which is my integrand. Well, that I think that will not be necessary here. So, let me just delete that. So, all I need is this observation. So, note this. So, the result is, so there is lots of arguments which, and students can follow the textbooks that we are following, but the main result is that to find the conjugate points, all we need to do is to look at the solution to the Jacobi accessory equation, and those are found by differentiating this extremal solution with respect to these constants, right. For different constants, we are going to get different family of solutions. All we need to find is the variation of these family with respect to these constants respectively. So, the result is as follows. In order to find the conjugate points, we have to find the solution to the Jacobi accessory equation. We can obtain a solution to the Jacobi accessory equation by differentiating the general solution of Euler-Lagrange equation with respect to C1 and C2, by differentiating the general solution of Euler-Lagrange equation with respect to my constant C1 and C2, right, or which means that my general solution U1 of x comma k, right, k will be k will be my other parameters in the function, right. So, or let me just call it as U1 of x. So, my U1 of x is partial y partial C1, and my second solution u2 is partial y partial C2. Students can check that these are indeed the solution to the Jacobi accessory equation, right. So which means that my general solution from here I get that my general solution to the Jacobi accessory equation is u, which is alpha times u1 plus beta times u2, right. Now, suppose for these solutions to the Jacobi accessory equation there are conjugate points, right. So, we are trying to find the condition for determining the conjugate points, right. So, suppose there are conjugate points, so if kappa, let us say, not equal to x naught is a point which is conjugate, this is a point conjugate to x naught, then there exists certain constants alpha beta which are all constants, both not equal to 0, right, both not equal to 0, such that the solution to the JAE, a Jacobi accessory equation, vanishes at these 2 points, such that u of x naught, which is alpha of u1 of x naught plus beta of u2 at x naught is equal to 0. These points x naught and kappa must be the roots of the solution, and u at kappa, which is alpha u1 kappa plus beta u2 kappa, this is equal to 0, right. Certainly, we have avoided the trivial equality by assuming that these constants are such that not both are 0, right. So, we have a unique solution to this problem, and the unique solution is not the trivial solution, not the 0 solution. So, from here I can see that I can solve this system of equation. So, we can solve for the unknowns alpha and beta, right. We can solve for unknowns alpha and beta, and we can get the following result. The result says that u2 of kappa times u1 at x0 is equal to u2 at x0 times u1 at kappa, and this so that is what we are after. Now, suppose at one of the points, the solution does not vanish, right. So this is my condition that we are after. So let me call this condition. So this is the condition for my existence of conjugate points. Okay. So that this is the condition that we were after. So solving this will give us our conjugate points. Okay. So let us look at this idea with the help of an example. Okay. So let my functional j be, again this is the same example that we are writing, is the same example that we began with in this lecture. So let j be the integral from 0 to L of y prime square minus y square dx, right. And for this functional, I see that my integrand is y prime square minus y square, or I see that the solution to the Euler-Lagrange, the Euler-Lagrange solution will give me that u is, well, the extremal y is C1 times cos of x plus C2 times sin of x, right. So I can see that the functions cos of x and sin of x, they are the solution to the Jacobi accessory equation by the discussion above that we have done. Okay. So, what we have is the following. So, let me call this, denote these two functions u1 by del y del c 1 is equal to cos of x. So, that is my first solution, and u2 which is del y del c2 which is sin of x is my second solution, right. So, my two solutions here are for the Jacobi accessory equation are these following. So, let us look at one of the solutions here, the sin of x. Note that the sin of x certainly vanishes at one endpoint 0, and it also vanishes at another point pi, and suppose let us also assume that L is greater than pi, right. So, what we have is the following. Consider my u2 which is equal to sin of x, right. So, any point which kappa which is conjugate to 0 for u2 will satisfy this starred relation above, right. So, what I have is the following: any point kappa conjugate, so kappa not equal to 0, but conjugate to 0, any point kappa conjugate to 0 will satisfy my starred conjugacy condition u2 at kappa times u1 u2 at kappa, let me denote, u2 at kappa times u2 at 0 is equal to I have two results u1 and u2. So, u2 at kappa times u1 at 0 is u1 at kappa times u2 at 0, right. So, from here I am going to get that this result will tell me that sin kappa, the point conjugate to 0, must satisfy this equation, and the solution to this equation is kappa is equal to plus minus n pi. Now, certainly if my domain is bigger than pi, then it implies that pi is, which is not equal to 0, is a point conjugate to 0. So, the conclusion out of all this discussion is that the extremal that we will get will so we have found a point conjugate to 0, right, and later on we will see that for the same example, the moment we are able to find non-zero or non-equal conjugate points, we are guaranteed that the extremal that we will get is neither the max nor the min, right. But so that concludes this example. Okay, so let us also look at another example, namely the geodesics on the plane. We know that the extremals are straight line, geodesic on a plane. So, my functional is my arc length functional, square root of 1 plus y prime square dx, my arc length functional, and my general extremal solution, my extremal solution y of x comma c1 comma c2 is c1x plus c2, right. So, my extremal solution is of this form. I know that these are straight lines, and I also, so I can see that the solution to the Jacobi accessory equation here is u1 is x and u2 is a constant, let us say 1. So, again if I use my starred condition from star, let us say kappa not equal to x0 is conjugate to x0. If I use my starred condition, I will see that I quickly satisfy the condition that the conjugacy condition is kappa is equal to x0, right, the starred condition. But that is itself a contradiction, because we assumed that kappa is not equal to x0, right. So, which means that no points conjugate to x naught, right, or in other words further check that my strengthened Legendre condition is also satisfied here. So, then it means that that the extremal that we get, the straight lines are a local minima, right, or a weak local minima, which means that y of x comma c1 comma c2, they are weak local minima. Okay. They are weak local minima. Okay. So, we can see the power of the second variation now. The moment we are able to find the extremal, we can determine under certain criteria, we can determine whether the extremal we have got is a local minima or not. Okay. So, let us look at another example, the case of the catenary. Okay. So, this is the case of the catenary. Okay. So, what we have is the following. So, we consider the functional, let us consider the functional with the integrand with my integrand f of x comma y prime, which is given to be y times 1 plus y prime square. So, I right away work with this integrand and my x is on the interval 0 to 1, right. So, I know that the general solution to this catenary problem is y of x comma c1 comma c2 is given by c1 cos hyperbolic of x by c1 plus c2, right. Now, let me call this as R1 because I am going to refer it later on, and I know that the solution to the Jacobi accessory equation will be the respective derivatives with respect to C1 and C2. I see that U1 is del y del C1, which will give me cos hyperbolic of x by C1 plus C2 minus x by C1 plus C2 times sin hyperbolic of x by C1 plus C2, right. And finally, my U2, which is the partial derivative of y with respect to C2, is minus sin hyperbolic of x by C1 plus C2. So, let me call this result, and so we have the boundary conditions, which are y of 0 is equal to y of 1 is equal to let us say 1. I call these boundary conditions as my R2, and I call these solutions to the Jacobi accessory equation as my R3. Okay. So, then we can use the boundary condition to find these constants C1 and C2. So, from my condition R1 and R2, I must have that the constants must satisfy this relation cos hyperbolic C2 is equal to cos hyperbolic of cos hyperbolic C2 plus C2, right. Or I can get that cos hyperbolic C2 is equal to minus 2 C2, right. I can directly solve. So, this is my transcendental equation that I solve. I know that there are two solutions to this problem. Let me denote those two solutions. One of the solutions C2 star is given by C2 star equal to minus 0.6, and the other let me denote it by C2 of, well, let me denote it by C2 1, this is minus 0.6, and the other solution I get is minus 2.1, right. That is the solution to this two equations. Now, we can substitute these values of the constant into our Jacobi accessory equation, and we are going to get, so from my R3 I am going to get my Jacobi accessory equation solution as follows. So, U1 is equal to cos hyperbolic of C2 of 1 minus 2x minus C2 times 1 minus 2x times sin hyperbolic of C2 times 1 minus 2x, and my second solution is minus sin hyperbolic of C2 times 1 minus 2x. Okay. So, then let me just make a substitution of variable. I am going to substitute C2 times 1 minus 2x as my new variable xi. Okay. So, let my xi to be equal to C2 times 1 minus 2x, and then it implies that if I were to find the point conjugate to 0, any point conjugate to 0 will satisfy the following conjugacy condition. I just plug in the point 0, I see that the following holds. So, what have we got? We have the following condition: cos hyperbolic C2 minus sin C2 sin hyperbolic C2 times sin hyperbolic xi, right. So, when we plug in 0, so when we plug in x equal to 0, I get that xi is equal to C2, right. So, that is why I get this one of the points. Okay. Okay. So, then the condition is this is equal to cos hyperbolic xi minus xi times sin hyperbolic xi, right. This is times sin hyperbolic C2. So, we can cross divide by sinh xi and sinh C2. I see that the relation reduces to the following: cot hyperbolic of C2 minus C2 is cot hyperbolic of C2, well, not C2, but xi minus xi. Okay. Okay. So, then let me call this as my condition R5, because we already have R, well, we already have, where is my R4? Well, I also need the condition R4. The R4 is the relation between C1 and C2, right. So, when I use, well, I also need to mention the following: using this condition R, this, let me call this as condition star. So, using star and my boundary condition R2, I can see the relation between C1 and C2. So, let me say that using R2 and my star, I can see that my C1 satisfies the following. So, 1 over C1 is cos hyperbolic of C2, which is minus 2 C2, and I call this result as R4, right. So, that is the relation between C1 and C2. So, we see that R4 itself has two solutions that we have mentioned, and for a fixed C2, let me say that for my first solution, I am talking about now star, right. So, for my solution C2 given by C2 of 1, which is minus 0.6, right. For this solution to my R4, there are two solutions, remember that. For the first solution, I can immediately see that R5, this conjugacy condition has two roots, right. Well, one of the root is xi being C2 itself, that is corresponding to when x is 0. So, xi is C2, and the second root is when C2, so then when C2 is C2 of 1, I see that the second root is also at x equal to 2.4, right. So, the second root to this equation R5 is at x equal to 2.4, but the most important part is that this does not lie in the interval from 0 to 1, or what we see is that there are no roots, no non-trivial roots which are conjugate to point 0 for the first case, right. So, what we have got is also students can check that the strengthened Legendre condition is true. Strengthened Legendre condition holds for any constant C2. So, that is not a problem. And since so let me call this as my case A. From case A, there does not exist a point conjugate to 0 in the open interval from 0 to 1, right. The only point conjugate is outside the interval, which means that the solution that I am going to get is a weak local minima, right. So, which means that the solution, the extremal that I am going to get, which is y1, which is equal to negative 1 by 2 C2 of 1 cos hyperbolic of C2 of 1 times 1 minus 2x is a weak local minima, right. We can do a similar exercise for the second case. For the second case, where C2 of 2 was the second solution to R to star or R4 was negative 2.1, we see that this leads to that x is equal to 0.6, which lies in the interval from 0 to 1, is coming out to be a point conjugate to 0, okay, or conjugate to 0, satisfying. So, it is satisfying my condition R5, right. So, R5 is my conjugacy condition. So, we have found a point which is conjugate to 0, or the conclusion is that the solution or the extremal y2, which is given by negative 1 by 2 C2 of 2 from the second constant here, cos hyperbolic of C2 of 2 times 1 minus 2x, this solution is neither going to give me a minima nor going to give me a maxima, okay, maxima for J, right. Okay. So, that concludes our discussion on the determination of the nature of the extrema using the existence or non-existence of conjugate points. In my next topic, I am going to look at what do we mean by, or what is the geometric interpretation of conjugate points, and further we are going to look at a specific class of functional, namely functional which contains convex integrands. And towards the later half of the next lecture, we will diversify all our theory into the development of the problems in optimal control theory. Thank you very much for listening. Thank you very much.